Let us talk about the serial input parallel output shift register. Serial input parallel output shift register. What is this one? Yes, this is if you can go back to the previous slide, serial input, serial output registers. So what we are doing here? Here we are giving the serial input register data, and we are taking output from here only. If somehow we can take the output from all this one, so that will become the serial input parallel output. This is the only difference. Okay, let me repeat it again what I'm saying. I am giving the data serially, and here I am taking out the data only from the Q0. But if I can take the data from this Q1, Q2, and Q3 as well, then this will become the parallel output. Okay, so this is the only change that is needed to make this logic as a serial input parallel output. Okay, there is no change in the logic, there is no change in the structure. That just you have to consider at which point I have to take the output. That's it. Okay, so for that purpose, what we need, I need one AND gate may be needed. Okay, one AND gate may be needed here, and that will be connected. And the second, yeah, one AND gate here, one AND gate will be here, and one AND gate will be here. Okay, and all the other, and these all are the outputs. Okay, and these all the one of the input of this AND gate, that will be controlled whether I have to decide if I have to make it as a serial or it's the parallel output. So if this is the control signal, and if this C is equal to 0, what it means, these three output will be 0. Okay, we will not get the output here, we'll always get the output here only. Even though there is output, but I will not get output here because C is equal to 0. So if C is equal to 0, I can make it is the serial input, serial output. And if C is equal to 1, serial input and the parallel output is possible, because this C is equal to 1. So this AND gate will pass this Q1, Q0 to the output side. So this is the only module that I have to add. Okay, so let us try to see how it works. Yeah, so this is the only concept that you should understand what we have done. Okay, so let us go back to that slide. Yeah, here. So you need AND gate that will decide whether I have to take the output or not. So you need some additional modules, something like this one. So this module is needed to decide the which kind of output I want. Like I want the parallel output or the serial output. So if the read input is equal to 0, then it will be the serial input, serial output. And if read is equal to 1, R is equal to 1, then it will become serial input, parallel output. So this is the only difference. Okay, rest all other are same. Okay, so that we have to consider. So this model similarly, yeah, so left shift and the right shift we can decide here, right? So here serial input is given to the least significant bit, so this is the right shift register. Okay, and here the serial input is given to the most significant bit, so we can call them, this is the left shift register. Okay, and so these two are the circuit for left and right shift register for serial input and the parallel output. Okay, but again the same circuit can be considered as a serial input, parallel output, and a serial input, serial output based on this activation. Okay, so this is how it is different. Okay. If anyone has any doubt, you can ask the questions. Now the next thing is the parallel input, serial output, left shift register. So here what I have to do, I have to just take all the input at the same time, and output will be taken out at the same time. So this is quite easy actually, it's not that much difficult. Input will be common. See here, if we see this particular diagram, this all are the lower part is nothing but this is the register part, and upper part decides whether I have to take it as a input or not, right? So if S is equal to 0, then these blocks or these inputs will be selected. So whatever the data I will provide, that will be loaded here. Okay, that will be loaded to the D0. Okay, now if this shift is equal to 1 or shift load is equal to 1, then what will happen? This will, because this output has been connected to the next input, so something like this. Okay, so whatever the data I have to write, so if this signal is equal to 1, so that will load the data here, that will be loaded, and when shift is equal to 0, then that will be shifted. Let me repeat it again what I'm saying. Okay, this is important actually. Okay, how it is performing? Suppose this input s is equal to 1. Okay, if this s is equal to 1, then what it will do? This x0, x1, x2, x3, these will be transferred to the d0, d1, d2, and the d3. Okay, what it means? Whatever the data I will provide, that will be loaded to the flip-flops. Okay, now whatever the data we have, that will be loaded. So if s is equal to 1, then the data will be loaded. Now if s is equal to 0, then what will happen? Whatever the data here I have, so there is no operation with this one. Okay, then if it is like this, like if shift or load input is equal to 0, then this I01 will be shifted over here. Okay, and this I01 need to be activated. So I01 need to be activated, and I01 is nothing but this is the output of the first flip-flop. So this Q0 will be shifted to the D0, Q1 will be shifted to the D2, and the Q2 will be shifted to the D3. What it means? The shifting kind of operation is performing. So the data input we are making the parallelly, the input data is parallelly, but the shifting is the serially, like serial output data is the serially. So this is how you can load and transfer, load and transfer, load and shift, load and shift. So at it, instead of time, you have to load it, shift one bit to the right. So something like that. This is how you can make it the parallel input serial output left shift register. Okay, left why? Because we are taking output from the MSB, which is the Q3. So that is why we are saying it the left shift register. So if anyone has any doubt, you can ask the questions here. Okay. So if there is no doubt, similarly, you can also make the right shift register. So instead of D3, you can make the output at the Q0. That's it. Okay, so this is the similar to that one. And the two modules will be needed, like this lower part is the register and the upper part is the control, like where I have to shift it. Okay, so the Q3 is shifted to the this D2, this D2, and Q2 is shifted to the D1, and so on. So what it means, we are shifting in the right direction. The rest all others are same like what we did before. So the load and control decides like whether I have to load or I have to shift. So this is decided by this one, and the same working as the previous slide. Okay, so this is how we can make the parallel input serial output shift register. Yeah, so I'm going in the faster pace, but if anyone has any doubt at any point of time, because see, all the circuits are similar, same, so I don't need to spend too much time on this, right? So that is why I'm just moving this pace. Because if you are able to understand the concept of register, so all the other things are easily doable. So this you can do it, it's not a problem. Now let us talk about the parallel input parallel output register with the load control. How we can make the parallel input parallel output. Okay, yes, again, with the load control, if there is no load control, then what will be there? Simply what we have already studied in the first slide, that is the parallel input parallel output. Let me go back to that one. What we have done here, see here, if you see this particular diagram, this is nothing but we are parallelly adding the data, and we are taking output the data parallelly. Okay, so this is what we are doing here. Okay, and this is nothing but this is a parallel input, parallel output kind of shift register. Okay, so this is the simplest parallel input, parallel output shift register. But if you want to make it controlled, then you can have something like this. Okay, so see here, if you want to load the data, just load and transfer, load and transfer. So for that purpose, what I have to do, if I want to, if let us assume if load is equal to 0. Okay, if load is equal to 0, what it means? Here I will get 1, here I will get 0. Okay, so if load is equal to 0, this will not be activated, this will not be activated, this will not be activated, this will not be activated. Okay, now if these all are not activated, so what it means, whatever the data we have, A3, A2, A1, A0, this will be loaded because this is 1. So these all will be activated and they will transfer to D3, D2, D1 and D0. So if load is equal to 0, the data will be loaded on the flip-flop. Okay, now let us see if load is equal to 1, then what will happen? If load is equal to 1, in this case, this will be in on state, this will be in off state, on, off, on, off, on and off. Now, if it is on, then what will happen? This Q3 is nothing but this is connected to this one and that will transfer D3. What it means? It will hold the same data. Okay, so load and hold, load and hold. So it will reflect the same data what we have given. Okay, so this is how you can make the controllable with the loading effect. Okay, so this is the importance. So here what we are doing, here we are parallelly loading the data first and then we are transferring, we are holding the data, load and hold, load and hold. So the load and hold is decided based on this control signal. So if load signal is equal to 0, then it will load the data from A0, A1, A2, A3 and that will transfer to the flip-flop. And if load is equal to 1, then that will hold the data, even though there is a change in A0, A1, A2, A3, but it will not be reflected at the output. Okay, and this is how we can control the data in the memory. In the first circuit, which we saw like parallel input, parallel output, there was no control. If there is change in the input, output will be changed. Okay, but if I want to make hold some of the data, then it is mandatory to have some control circuitry. Okay, so these are the control, this is the memory and these are the control circuitry that are responsible to either hold the data or to transfer the data or to load the data. So this is the important part that you have to understand, how this parallel input, parallel output register is with load control is different from the first circuit. Okay, so this is how it is different. Okay, so if anyone has any doubt, yeah, this is how you can make the truth table. Like if the clock is equal to anything, if the clear is equal to 0, the data output will always be 0. It does not matter what is the status of load, status of clock, or status of input. Okay, and if the load is equal to 1, then it will hold the data. If load is equal to 0, it will load the data. So this is a simple table which we have already seen here. Okay, so this is all about the parallel input, parallel output register with load control. Now let us talk about the universal shift register. As of now, we have studied left shift register, right shift register, serial input, serial output, parallel input, parallel output. So all these things can be made over here. Okay, so let us try to see here. Because I can perform the parallel loading, I can perform the left shift, I can perform the right shift, I can perform the hold operation. So for all these operations, I just need to combine whatever the concept we have studied. Because if I want to perform 4 operations, I need 4:1 marks here. There is a mistake. It should not be the 2:1. It should be 4:1 marks. Okay, 4:1 marks is needed. And based on the control signal, like let us assume S0 and these are the 0, 0. So let me change the color. So if these S0 and S1 are the 0, 0, then this one, this one, this one, and this one will be selected. Okay, if these are selected, what it means, whatever the data I have here, that will be transferred to the D flip-flop, and then accordingly I will take the output. Okay, and because see here, this is control, and then output is taken from here only, so the serial output this is. So parallel loading is possible, and the serial output is possible. Similarly, if we are changing the 1 0 or 1 1 or 0 1, accordingly you can select like what kind of operation it is. So this particular diagram is nothing but this is the combination of all the circuit which we have studied before. Okay, and based on that, the control signals are deciding what kind of operation I have to perform, whether I have to perform the load operation, or I have to perform the left shift or right shift, or I have to hold the data. Let us try to check this one, 1 1. So if it is 1 1, what it means, these will be selected. This will be selected. What it means, this I3 is nothing but this is connected to the output. This is connected to this output. This is connected to this output. What it means, they are holding the data. Okay, so this is quite simple. It's not that much difficult. We can understand what kind of operations we are performing. So based on the control signals, you can decide whether it is left shift register, right shift register, parallel loading, or the holding one. So this is what the operation of this circuit is. Okay, take some time to understand these things, and then you will be able to understand. Okay, so this is all about the 4-bit universal shift register. Okay. Let us take one example. Can we extend this for only 5 minutes? Because let me ask to the LMS team whether they are free for some time for 5 minutes or not. Okay, otherwise I need to just close it because only 2 slides are left. I can finish it. Okay, so let us continue for 5 more minutes. I have just taken the approval from the LMS team because just I need to finish this part in the continuation, so that I should not wait for the next lecture to finish this part. Okay, so let us try to understand this one. I will just finish by 11:30. Sorry, 10:30. Only I will take 6 minutes. Okay. So if you see here, based on the input combinations, you can just decide which kind of operations I have to consider. Let us consider one more example. If I'm considering 0 1, okay, 0 1 means what? This will be selected. These inputs will be selected. And if this input will be selected, let us see here, I am giving the input, and input is connected to this B0. What it means, this is the LSB. Okay, and if it is the LSB and it is shifting, and again I'm taking the output from here only. Okay, output, if you can see here, Q bar and this bubble, what it means, I will get the output from here. Q bar is nothing but this is complementary of Q0, and again one inverter will give you the exact output what we want. Okay, so this is how what output I will get, and because we are providing the serial input here, the serial input means the shifting will be in the left direction. So the based on controllability, you can check it out what kind of output I will see here. So this is really very important thing that we should understand. So I'm giving 1 minute time to think, and then please look into it, and then I will move ahead with one example. Okay, fine. So if you do not have any questions, let us take one example here. What this problem says: a 4-bit shift register circuit configured for right shift operation. Right shift operation means that need to be shift in this direction. Okay, means B in will be connected to A will be shifted to B is shifted to C, and C is shifted to D. If the present state of the shift register ABCD is 1101, so what is the state? How many clock cycles are required to reach the state of 1111? Okay, so let us try to see it, how many clock pulses are needed. Okay, so see here, I have a 4 inputs A, B, C, 4 bits, and the initial data was 1101. Okay, 1101. Now let us assume the clock. Okay, so it required the clock pulse. The first clock pulse, after the first clock pulse, what I will get, this D in, yeah, so for that purpose you need to XOR the logic. Okay, so if I have to XOR the D, this D and A need to be XORed, and that need to be connected to the A. So this is the operation what I have to do. Okay, and we know that for XORing like 0001 1011, the output is 0110. Okay, so this is the output that required. So for the after first clock pulse, what output I will get? This C will be shifted to the D, so this will become 0. B will be shifted to C 1. A will be shifted to B 1, and what will be the A? That depends on what is the status of this one. So 1 and 1, 1 1 means that will give you the 0. Okay, so 1 1 0. Now let us talk about the second clock. This will be here 1 1 0, and I have to XOR 0 and 0, so that will give you the 0. And it will be like 1 0 0 and 0 and 1 1. Then 0 0 1 and 1 1 will be 0, and 0 1 0, and that will be 0, and then 1 0 0 and 0. I think this is correct. And the next one is 6 1 will give you 0 0 0 and 1. 7th will give 0 0 1 1. 8th will give 0 1 1, and then 1 0, this will give 1, and 9th will give, yes, this is now correct. So 1 1 1 and 1. So it required 9 clock pulses. Sorry, I made a mistake here at step 2. So total number of 9 clock pulses are needed to get ABCD 1111. I think this is correct, right? Thank you for correcting. Okay, so if anyone has any doubt at this point, you can ask the questions, because yeah, this is very easy actually, not difficult. Just we have to do some operations, and then that is doable. So you need 9 clock pulses, 9 clock cycles are needed to make it 1111. Okay, similarly we can have one example here. The similar kind of approach will be utilized. So I'm just giving you an example. You can do it at home. Like, what will be the content of shift register after 3 clock pulses? So here in the previous example, what I said, I just wanted to, what is the status, like this value after how many clock pulses. But in the next one, I have already given the clock pulses, and I need to check what is the status of output. Okay, so initial value is this one, and after 3 clock pulse, what is the output? You can tell us. And the second part is how many clock pulses is needed to make it 0 0 0. So this is what we have already done it in the previous one. Okay, so this is what you can do. Okay, and now this is some of the tutorial questions that you have to solve.